Dear friends, students and learners, I am Shashank from the School of Engineering and Technology in the Gandhi National Open University. So in continuation with the previous session where we discussed up to the refractory metals, now we will discuss about certain of these refractory metals and their alloys, the properties and their applications. Now further we discuss the niobium and its alloys. So this metal actually has the lowest melting point among the 5 refractory elements which we will be discussing in this session. So the melting point is 2468 degrees centigrade and its density of 8570 kg per meter cube is also the lowest among these elements. But it has got certain applications which I am discussing with you. And the niobium can be used as alloying element for microalloyed steels, stabilized stainless steels, and as solid solution alloying addition to many nickel-based superalloys. And Inconel is one such example. Inconel is a very famous thing which is used for various purposes, even in the aerospace industry. So niobium alloys are employed in aerospace and missile applications because it has the property of low density and it has also got high strength at elevated temperatures. And it is further used in superconducting alloy with Ti, that is titanium. Many alloys of NB are prepared by adding such elements as zirconium, titanium, hafnium and tantalum, and these alloys actually are made by vacuum arc melting process. Then there is one very special alloy of niobium that is called the C103, and its content is like niobium is 10%, hafnium is 1% and titanium is 0.75% and a little zirconium is also there, and it is used to replace weaker NB alloys because it gives better formability and welding properties. So forming is a process in manufacturing and welding is also a process, so it gets better if such an alloy is used. This alloy is coated for oxidation resistance for use in rocket applications also, requiring moderate strength at temperatures of about 100 to 1370 degrees centigrade. So it is very much used in the space and aerospace industry, and some alloys have better strength than that of even C103 which we discussed right now at elevated temperatures, like the C129Y is there and its content is there which you can read from your study material also. Then we have the FS85 and CV752. So these are the different types of niobium based alloys, and all these 3 alloys can be fabricated. They are thermally stable and can be protected against oxidation by coating. Also these alloys with protection from oxidation find numerous use in making rocket nozzles, gas turbines and guidance structure for re-entry vehicles. After discussing the niobium, we move on to the tantalum and its alloys. So now this tantalum has a slightly higher melting point than niobium, and it is 2996 degrees centigrade, and its melting point is less than that of only tungsten and rhenium. Despite its high melting point, tantalum is easily workable at room temperature as its ductile brittle transition temperature is very low. So like we read just before this, that tantalum is very good even at low temperatures of around 4 Kelvin. It maintains its ductility. So the same thing here. Because of its high corrosion resistance, tantalum is used in chemical process industry as well, and major use of tantalum is in electronic industry as capacitor. So it can store charge. That's why as capacitor it can be used. And at about 150 degrees centigrade, tantalum forms a thin but a stable oxide film on the surface. This film obstructs further oxidation and thus renders material resistant to corrosion. So it is a very good property that it can protect itself by making an oxide film around 150 degrees centigrade. But the drawbacks are also there, like its cost is a major hindrance. It is very costly, and it is attacked by hydrofluoric acid as well and sulfur dioxide. In such heat exchanges where at least one medium is corrosive, tantalum is preferably used. If both are corrosive, we won't be able to use it. Then the capability of tantalum to form the solid solution with tungsten and niobium results in alloys with improved strength. Like we discussed earlier also, that alloys are far better, but their susceptibility to oxidation is also increased if we are mixing all these things. So then oxidation becomes a dangerous thing. It can't prevent oxidation after it is mixed with the tungsten and niobium. So they can be used only above 480 degrees centigrade with protective coating only. Tantalum alloys are used from 1370 to 1980 degrees centigrade, and there are certain common alloys with the name of TA10W, then TA40NB, TA8W2HF. So all these things you can see from your study material. The first and third of the above alloys which I told just now, these are used as high temperature component in spacecraft and propulsion engines. So basically all these things are used in the spacecraft industry, where high temperature always comes in. And this TA10W alloy offers the advantage of room temperature fabricability. After discussing tantalum, the next one is the molybdenum. And we have earlier also discussed molybdenum. It's a very famous element, and its alloys in the previous sessions also. So a little bit here also I'm going to tell about this molybdenum. It's very commonly available and the least expensive element of the refractory metals. So it is least expensive out of the 4 or 5 which we are discussing here. That's why its use is very common. And MO is added to low alloy steel, tool steels, cast irons, stainless steel and super alloys as alloying element. And it is the following effects, like it increases the toughness and hardenability of low alloy steels, like we have discussed during the previous session of the steels. And it increases corrosion resistance of stainless steel, increases high temperature strength and corrosion resistance of super alloys as well. What drawback it has? The difficulty with MO is that its brittleness at room temperature, and which has greatly reduced its possibility of widespread application. So at room temperature this molybdenum becomes brittle. One of the alloys of this molybdenum, that is the TZM alloy, offers better behavior at elevated temperature than an alloyed MO, since MO loses strength due to softening and recrystallization. So that's why TZM alloy becomes better than molybdenum. And this alloy has creep resistance which is also very high, above 1000 degrees centigrade. The TZM alloy strengthening occurs due to the precipitation of the complex molybdenum, titanium and zirconium carbides. So this TZM alloy is formed from these elements and by the precipitation of these elements. And it has been found that high temperature behavior of TZM can be further improved by night riding process. So if we do night riding process, then TZM can even get better. Then we are moving to the higher side of melting point, the tungsten comes in. So tungsten has the highest melting point temperature, which is around 3410 degrees centigrade, 3410 degrees centigrade, and its density is also the highest. Modulus of elasticity is also the best, and with oxidation coating, tungsten can be used as a structural material up to 2480 degrees centigrade. So it can be used in our rockets and space shuttles, etc. It has good dimensional stability at elevated temperature. And why it is so? Because of the low coefficient of thermal expansion, good thermal conductivity and low vapor pressure. So the residual stresses are not that much because of its good thermal conductivity and also low coefficient of thermal expansion. It is not distorted by the rise in temperature. Because of high density and melting point, tungsten forms alloys with only a few elements, one such as rhenium, which dissolves in tungsten up to 26%. Up to 5% rhenium in tungsten helps increase the hot strength, recrystallization temperature and electrical resistivity also. Rhenium addition also increases the low temperature ductility. So at low temperature our tungsten will become much more ductile if rhenium is there. So it is around 1.5% of rhenium, and tungsten about 3%. So two kind of alloys are there. Rhenium alloys are all used for lamp filaments and thermocouples. And hafnium is also used as an alloy. It is exceptionally high strength at elevated temperatures due to dispersion of carbide of hafnium. Thermionic electron emission of tungsten increases by addition of 1 to 2% of thoria. Thoria we have discussed earlier. It was an oxide, thorium oxide. So this alloy also has increased strength at high temperature. So if we want more thermionic electron emission, then we have to add thoria to tungsten. Then there are aqueous alloys of tungsten, which are basically tungsten 1% and thorium oxide also is there, and small amounts of aluminium, potassium and silicon are also there. So these alloys can be treated to attain recrystallization temperature greater than 1800 degrees centigrade. And these kind of alloys have long grains which tend to interlock, and long use at elevated temperature may not result in permanent deformation as is required in electric bulbs or lamps. Some alloys are described here, which I have mentioned to you. So after discussing all kinds of the refractory metals, we further move on to the abrasive machining process. This is also very important. The abrasive machining process are precision machining processes. They produce workpiece surfaces with a high degree of dimensional accuracy and surface smoothness. So suppose a machining has been done on a certain specimen, then you want further accuracy and further precision, or you want surface finish or smoothness, then this kind of process is very useful, the abrasive machining process. Rough grinding is sometimes used for removing excess material from the surface of the castings, forgings and similar workpiece which have not been machined. So as told earlier, that rough grinding is done if you want to remove excess material whose quantity is quite large. But further moving on, rough grinding won't be used. But in rough grinding, what we are using, a rotative abrasive grinding wheel which is guided manually relative to a workpiece surface. But this process actually differs from generally known grinding operation which is used for a smooth finish and close tolerance. Like I told you earlier, for a very smooth finish process, this rough grinding cannot be used. In that case, grinding tool is machine held and grinded in the case of rough grinding. Abrasive are also used on belts or powder paste. So further we are discussing this abrasives which are hard materials with adequate toughness. So both properties are there, like they may be hard from outside, but there is certain softness inside, so that they don't break. A number of materials may serve as abrasive, but in the abrasive machining process basically three types are there, which first one is the diamond, which is a form of pure carbon. The second one is the silicon carbide, SiC, and the third one is the aluminum oxide, Al2O3. So we are now discussing the first one, diamond. So diamond is a hardness of 10, that is its perfect hardness on the Mohs scale, but it is very high cost. We all know, everybody wants to have diamond. Used only for those applications which require its use and justify its higher cost. And diamond is one of the natural abrasives which is found in the earth's surface. Next one is the aluminum oxide. So it has varying proportion of impurities and it is also found as a natural abrasive. However, in order to control purity and secure uniformity, practically all of the aluminum oxide and all of the silicon carbide used today in the abrasive machining process are produced synthetically. So it is a natural one, but it has been produced synthetically in order to control different parameters. Then the third one is the silicon carbide. It is somewhat harder than the aluminum oxide, but aluminum oxide actually it gets better in case of toughness. It is tougher than silicon carbide, with the result that its grains will not fracture as readily as the SiC. So applications, some of the applications are like aluminum oxide is used for grinding steels, malleable iron and other materials with high tensile strength. whereas silicon carbide is employed for grinding cast iron, bronze, aluminum casting and other materials with low tensile strength. So we can see alumina for high tensile strength and silicon carbide for low tensile strength. Green SiC is another kind which is 99% of SiC, and it is used to grind cementite carbide. And how are these abrasives produced? Now we will see these things. Abrasive material, whether we are producing it synthetically or whether it is found in nature, both are taken up and they are crushed to particles of the desired size. So crushing takes place, and these particles, these small particles are known as the grains or the grits. For some kinds of application, the crushing is continued until the abrasive becomes a fine powder. So depending upon our need, it may be further crushed, and on further crushing it is somewhat just like our floor, kitchen floor that we are using. Like sands, abrasive grains are passed through a set of standard mesh sieves to separate them according to the grain size. So we can then define the grains according to their sizes, and for that purpose they are passed through a standard mesh sieve. Grain size is designated by the mesh or the finest standard sieve through which the grains will pass. The size is described by a number of meshes per linear inch. The standard meshes are from 10 to 600 of size, and this size is also known as the grit size code. Coarse and medium size grits are used for soft material, whereas fine and very fine size are used for the hard materials. Abrasive floors, which are too fine for separating with sieves, they need to be segregated by a flotation method in a liquid. So the size of this may become even smaller than the size of the sieve. So in that case we will be using a different method, that is flotation method. Abrasive may be used as loose grains or floors, as in lapping, polishing and buffing. So it can be used in different purposes, lapping, polishing and buffing, but their types may be different. For grinding, honing and super finishing, the abrasive grains are bonded together into shapes known as the grinding wheels, sticks and stones. So for these kinds of process, super finishing and all, the wheels are made, grinding wheels are made. Abrasive grains, when suitably held and moved across a certain workpiece surface, they will remove material by a cutting action, and this cutting action produces minute chips, and it is actually similar to the cutting action of other cutting tools. So cutting is done by other tools also, but there the amount of material removed was quite larger. So here we are doing a finishing type of thing, but the process will remain the same. The cutting is taking place in the same fashion, but the size may be very small, chips, minute chips will be there. Grinding is a process. It's a very important process, and we can know about this now. Grinding is accomplished with the use of an abrasive grinding wheel mounted on a suitable machine and rotated at a suitable rotational velocity. In precision grinding, movements of the grinding wheels relative to the workpiece are accurately guided by the machine. Grinding is done on a workpiece for three major reasons. The first one is to machine materials which are too hard for other machining methods which use cutting tools. Then to produce surfaces within closer dimensional tolerances, and further to produce surfaces with a higher degree of smoothness. Like I told you earlier, here the material removal is very less, and it can be in the range of microns also. So with this we can get better tolerances and we can get a smoothness. So all this is the purpose of grinding. And what are the requirements for this grinding to take place? The economy of the grinding process actually depends upon the amount of material to be removed, our power requirements, then the labor costs and the tool costs. Materials harder than about Rockwell C45, which we read earlier, must be machined by grinding. So harder is the material, we will have to go for the grinding process. When a workpiece is to be hardened, the majority of the excess material should be removed by some other machining process, like told earlier also, prior to hardening. Only a minimum of excess material should be left on the workpiece surface to be removed by grinding after the hardening. This excess material is known as the grinding allowance. So this is the allowance. We will be knowing that after cutting it with a certain other tool, this grinding allowance has to be left. Then this can be done with the help of grinding wheel. Grinding allowance will have to be slightly larger for some workpieces, which may change shape slightly during heat treatment. So during heat treatment, some may be changing their shapes. So according to that, we will have to have larger grinding allowance. What are the advantages of grinding? So small size of the cutting edges on the grains will be there. Since the cutting takes place in exceedingly small amount, it can be controlled also to hold close dimensional tolerances, and also it produces smooth surfaces. Workpiece of either hard or soft materials are often ground to take advantage of this ability of grinding. Dimensional tolerances as small as 0.0025 meter and surface smoothness of 0.025 meter are easily obtained by grinding. Like told earlier, very small sizes or smoothness can be maintained. By using better than average equipment and skill and care, even better dimensional tolerances, even smaller tolerances can be achieved. Now a bit of discussion about the grinding wheels, and this was made first thoroughly mixing proper size grains of the desired abrasive with the bonding material. Like we used alumina and silicon carbide, so these are the raw materials, and all grain surfaces should be thoroughly coated with bonding material, and we have to bond them with each other, then we can form this grinding wheel. So the mixture is either then pressed or formed in molds to the desired shape and size. So we can use molds to give it a desired shape, whatever shape and size we require. After drawing these shapes from the mold, the bonding material must be hardened by heating or by other means. So we have to remove this material, so we can do heating, or there may be some other method also, mechanical method to remove it. The central hole of a grinding wheel, which fits an arbor, is pushed by pouring molten lead into the hole around a removable metal core. Then there is a phenomena called throwing, and what it is actually, it cuts a small amount of material from a surface of a grinding wheel so that it will become concentric with the axis of rotation. So suppose the wheel is not concentric with the axis of rotation, then this throwing process will take place, so that their centers, the grinding wheel center and the center of the shaft on which it is mounted, are both coinciding, they are together. And what are the materials actually? A little bit idea I gave you earlier. Now what is the constitution of grinding wheel in detail? So grinding wheels are made with inorganic bonds, which is vitrified or silicate, or organic bonds, which are the types of resinoid, rubber or shellac. So both types of things can be there, inorganic or organic bonds. Vitrified wheels, which use ceramic, porcelain as binder, are most commonly used, and these wheels can perform all types of grinding and micro finishing operations. Other binders include the refractory clay, feldspar and talc. They have high strength, and this is attained due to firing at high temperature. They are but brittle and hence cannot be made thin and long. Then there are the organic types one, the resinoid wheels. These are more flexible and stronger. Thin wheels of large diameter have this bond, and resinoid bonded wheels wear fast and they are destroyed in alkaline pools as well. So these are some drawbacks, and the bonds burn at temperature above 300 degrees centigrade. And then there are rubber bonded wheels, which are flexible and strong and can be used for slitting operations and centerless grinding, but they deteriorate around a temperature of about 150 degrees centigrade. Further, certain nomenclatures are there, like a grinding wheel should be marked to give the following information. What information should it give? What type of abrasive we are using, what is the abrasive grain size, what is the bonding material that has been put there in the wheel, and what is the structure of the grinding wheel. And what does the structure actually mean? A structure indicates how closely the abrasive grains with their bond coatings are packed together, meaning the contact between the abrasive grains and the bonds. So this is defined by the structure. Then there is grade also. It indicates how strongly the abrasive grains are held in the grinding wheel. The bonding material ordinarily does not occupy all of the space between the grains because it merely coats the grains. So there are gaps between the bonding material and the grains. So further discussion on structure and grade. So grains are held together at points of contact between the bond coating. So grains are held together, meaning they have the points of contact, they are held together at that point of contact. And grinding wheels are porous to varying degrees depending upon their structure. So porosity will come in. Suppose it's a kind of a structure where this bond is not allowing contact between the grains, then certain space will be left, so porosity will be there. Open spaces between the grains will help to provide room for chips and to carry cutting fluid to the area where the cutting occurs. So this porosity actually helps also, like we are seeing here. So the cooling fluid can move better, and the wheel will not get heated up or will not get damaged. The strength with which the grains are held in a grinding wheel depends upon the number of points of contact between grain bond coatings. So there is grain contact and there is grain bond contact also. So strength will depend upon the grain bond contact, and again on the strength of the grain to grain connection. This means that grade depends upon the structure and the kind of bonding material and the amount of bonding material that has been used. So it is dependent on all these things. And the grade of grinding wheel, that's why it is also referred as the hardness also. There are 3 grades of grinding wheels. The first one is the soft, and it is generally given by alphabets from A to H. Then there is the medium from T to P, and then the final one is the hard one from Q to Z. So generally what happens is that soft grades are used for the hard materials and the hard grades are used for the soft materials. Why? Because through common sense also we can see that the harder one will have more hardness, it will be able to extract the softer particle. Whereas the soft, if we use soft instead of the hard, then the soft one cannot track the soft, it may coalesce into that. So that's why for the soft one we are using the hard, and for the hard one we are using the soft one. So here you can see in this figure, the green particles represents the grains and the red ones represents the bond. So there is the grain to grain contact also, and there is the grain to bond contact also. So the structure or the grade will depend upon both the strength of both these connections, that is grain to grain as well as to grain to bond. So in this session we saw about the alumina silicate composites, then various methods of production of ceramics and carbides, and we also learnt about the glasses and how they are produced, what are their applications, and further we learnt about different kinds of refractory metals, what are their properties and their applications. Thank you very much.